All right, kiddos, welcome back. Today we're going to talk about electrochemistry. We're going to talk about an application of the reduction and oxidation process that we learned about in the previous chapter. So electrochemistry is the study of redox processes by which chemical energy is converted to electrical energy and vice versa. Now this is quite practical and has uses in industry and critically important for biological functions, as you may have learned in your biology classes. So we're first going to talk about something called Voltaic cells or Voltaic cells. These are often commonly called batteries. So let me define a Voltaic cell for you. This is an electrochemical cell that converts chemical energy into electrical energy and they do this by spontaneous, we've used that word before, haven't we? Redox, reduction, oxidation reactions. Okay, now the best way to show this is with the classic example, a zinc copper battery. Every chemistry textbook that you will ever see will have this particular example. We will have a zinc anode. I'll tell you what an anode is in just a minute. And it's submerged in a solution of zinc nitrate. And we have a copper cathode, so just a piece of copper, and I'll tell you what a cathode is in just a second. And that's immersed in a solution of copper 2 sulfate. Now the cells are connected by something called a salt bridge, and this salt bridge has potassium chloride in it. So it has K plus and Cl minus ions in that salt bridge. Now the first picture here, the salt bridge and wire provide an unbroken pathway for the electrical charge to flow. So here is my wire and the charge is just flowing. What we can actually do is we can have those electrons as they move do some useful work for us, and they could also light up a light bulb or some other practical use. So what we have here is a piece of zinc. Here's my zinc metal, kiddos. It's immersed in a solution of zinc nitrate. Now we don't care about the nitrate ions, they are spectators, but we do care about the zinc 2+ ions. Now in this electrode, oxidation is occurring. Now the electrode where oxidation occurs is called the anode. So since oxidation is occurring on the zinc electrode is called the anode. Now on the other side, we have a piece of copper metal, and that's immersed in a solution of copper 2 sulfate. The sulfate ions are also spectator ions, so we just care about the copper 2+ ions. Now in this electrode, you will find reduction is occurring. In the electrode where reduction occurs, it is known as the cathode. Now, it's easy to get the two confused. Like if I ask you, what is that electrode called where reduction occurs? You have a 50-50 chance, right? Anode or cathode. Well, when I was just a little guy, my teacher taught me sort of a silly way to remember it, and I'll teach you the same thing. You'll notice that oxidation, the word oxidation starts with a vowel, O, and so does anode, starts with the vowel A. Reduction starts with a consonant, in this case R, and so does the word cathode. So I've always remembered, sort of silly, isn't it, that the vowels go together. The anode is where oxidation occurs, and the cathode is where reduction occurs. The consonants also go together. So let's take a look at the anode reaction. The anode reaction is zinc metal becoming zinc 2+ ions. And in the process, 2 electrons are kicked off. Electrons are lost. That's an oxidation process. Remember, oxidation occurs at the anode. And if you look at the cathode reaction, we have copper 2+ ions that are in the solution. Remember the copper 2 sulfate solution, gaining 2 electrons. I wonder where those electrons came from. That's right, they came from the zinc electrode that lost them. And when copper 2 plus gains 2 electrons, it produces copper metal. Now you can see, just by these two reactions, that the zinc electrode is dissolving. It's producing zinc 2 plus ions, so its mass is decreasing. And the copper electrode's getting bigger because the copper 2 plus ions in solution are gaining 2 electrons, and they're making more and more copper metal. Now I can add these two equations together, so we're going to draw a line beneath them, and you'll notice the 2 electrons lost and the 2 electrons gained cancel out, and we end up with the overall reaction. We have zinc remaining and copper 2 plus, and we end up producing zinc 2 plus and copper metal. Notice when we do this, both the atoms and the charge are balanced, so that is a balanced redox reaction. Well, while we're here, let's go ahead and identify the substance oxidized, the substance reduced, the oxidizing and reducing agent. So you can see zinc starts out with an oxidation number of 0, copper, of course, 2 plus. Zinc ends up as 2 plus, and copper metal has an oxidation number of 0 on the product side. So it looks like zinc goes from 0 to 2 positive. So zinc was oxidized, folks, and copper 2 plus becomes copper metal. It had to gain 2 electrons to do that. So copper 2 plus was oxidized. Now, or reduced, excuse me. The oxidizing agent is the species reduced, so that would be copper 2 plus, and the reducing agent is the species oxidized, and that would be zinc metal. Now, before we turn the page, I want to look a little bit more at these cells here, at these batteries. Let's look at this one where they're lighting up the light bulb. I haven't written too much on that yet. So we know that zinc metal is oxidized. It forms zinc 2 plus ions, and in the process kicks out 2 electrons. Now those electrons flow through this wire, pass through the filament in that light bulb, and as they pass through, boy, they're moving through quickly, they're creating friction, and they cause that tungsten filament to begin to glow and emit light. And then they end up over here on this copper electrode where electrons are gained. So my copper 2 plus gains 2 electrons and becomes copper metal. Now, during this process, the anode, remember the electrode where oxidation occurs, the anode ends up losing electrons to form zinc 2 positive ions. This solution over here becomes more and more positive, doesn't it? And over here at the cathode, electrons are being gained, and so these positive 2 ions are being lost, and so the cathode's becoming less positive. So how do we balance the charge in those two beakers, in those two what we call cells? Well, since this side, my anode's becoming more and more positive, remember we have our potassium chloride salt bridge? The chloride ions will migrate through this, what we call a U-tube, into this beaker, the anode side, to balance the charge. And on the cathode side, remember these copper 2 pluses are becoming copper metal. So we're losing copper 2 pluses, so the potassium ions in the salt bridge will migrate towards the cathode side to balance the charge. So the purpose of that salt bridge is to balance the charge because positives are being produced or being lost depending upon what electrode you're dealing with. All right, let's go to the next page. What we're going to see here is a rather complicated looking table. It's always looked complicated to me. This table is called the Table of Standard Reduction Potentials. When we look at this table, we will notice that each species is gaining electrons, which we know is reduction. We're going to find out what an oxidation potential is and what that would look like in just a second. But let's take a look at these reduction potentials. Let's look at the two that we're dealing with in our battery on the previous page. Don't we have zinc 2 plus? And let's see, we also have copper 2 plus, and we have to find that. So let's go ahead and search for our copper 2 plus. It's right over there. Okay? Now, copper 2 plus gains 2 electrons to become copper metal. The potential for that occurring is what is a voltage of 0.3419, a positive potential. My zinc 2+ becoming zinc metal, so this reaction right over here has a potential of negative 0.7618. Now these potentials are what we call relative potentials. They are compared to each other. They are actually compared against what we call a standard. Physicists have decided that we would have a standard reduction potential of hydrogen ions gaining electrons to form hydrogen gas, and they have decided to say that that potential is 0.0000. And all of these other reactions are compared to it. If it's more easily reduced than hydrogen ions, it will have a positive reduction potential, as we see in my copper 2+. If it's not as easily reduced as my hydrogen ions, it has a negative reduction potential, as we see in the zinc 2+, gaining 2 electrons to become zinc. So we call this a relative scale. It's all comparative to this reaction right here, which we have decided to give a reduction potential of 0.00004. Now, if copper 2+ gaining 2 electrons to become copper has a standard reduction potential of positive, we'll round this off to the nearest thousandth, 0.342 volts, then what would be its oxidation potential? Well, the oxidation potential is the reverse reaction. So I would have copper becoming copper 2+ losing 2 electrons. And it turns out that the oxidation potential is the exact opposite of the reduction potential. The reaction's written backwards, so the sign is backwards as well. So the reduction potential is positive 0.342 volts. In order to go backwards and lose electrons, the oxidation potential is a negative 0.342 volts. Let's do the same for zinc. For zinc, we can look up at the chart above, and we see that zinc 2+ gaining 2 electrons to become zinc is a negative 0.762 volts. Once again, just rounding off to the nearest thousandth. So what would be the oxidation potential of zinc losing 2 electrons to become zinc 2+? That's right, it would be a positive 0.762 volts. So what you will see in your textbooks is you will commonly see standard reduction potential charts. You will never see standard oxidation potential charts because the publishers think that you're smart enough to figure out what the oxidation potential would be if you're given the reduction potential in that reaction. Remember, the oxidation process is the exact opposite of the reduction process, and so the signs for the potentials will change as well. Okay? All right, so in this next illustration here, we have our hydrogen ions in these two solutions, kiddos, being reduced to form hydrogen gas, and of course that has a reduction potential of 0.000. And you can see, since copper 2+ has a higher reduction potential than hydrogen ions do, remember it was a positive 0.3419, the electrons will flow from the hydrogen electrode towards the copper electrode because it has a stronger reduction potential. On the other hand, zinc 2+, as you recall, has a negative reduction potential. So that means the hydrogen ions have a stronger reduction potential. 0.000 is higher than negative 0.762. So the electrons will flow from the zinc electrode towards the hydrogen electrode. Well, great question comes up. What if we put copper and zinc together? What would the potential of that cell be, or that battery? Well, that's what we're going to find out right now. Let's calculate the cell potential for copper 2+ becoming copper and zinc becoming zinc 2+. So we know copper 2+ gaining 2 electrons to become copper has a reduction potential of, this is getting marked up quite a bit, 0.342. And my zinc, it's becoming oxidized, folks, is becoming zinc 2+ and 2 electrons. The oxidation potential of that is not negative 0.762. Remember, the oxidation potential is the backwards of this reduction potential, so it's a positive 0.762. So, if we add these reactions together, as we did earlier, we end up with a balanced redox equation. And it turns out if we add their oxidation and reduction potentials together, we get the overall potential for that cell. And so we end up with a 4, a 0, carry the 1, 1.104 volts. So it's a positive 1.104 volt battery. All right. Let's do a couple more of these. Let's calculate the cell potential for the following reduction half reactions that represent the half cells of a Voltaic cell. So I'm going to give you two reactions. I2, so this is an iodine cell gaining 2 electrons to become 2 I negatives, and Fe2+ gaining 2 electrons to become Fe. So one of these reactions will have to be oxidation, the other will have to be reduction. So let's look up the reduction potentials of both of these reactions to decide which one is reduced, and then the other one will be oxidized. So let's go to this page over here. Let's clear this up so it looks a little bit better. And let's find those two reactions. So we're looking for I2 gaining 2 electrons to become 2 I negatives. So let's see if we can find that. Here it is. All right, and the other reaction looks like it is Fe2+ gaining 2 electrons to become Fe. So see if we can find that one. And here it is, right over here. So let's write both of these reduction potentials down. So the iodine reaction is positive 0.536. So the iodine reaction was a positive 0.536 volts. And the iron reaction, the iron 2+, was a negative 0.447. Negative 0.447 volts. Now in a redox reaction, one thing is oxidized and one thing is reduced. We can't have both of them being reduced. So we have to decide which one is reduced and which one is oxidized. So the one that's reduced should be obvious. It's the one with the higher reduction potential. So let's go ahead and write that down as my reduction reaction. I2 plus 2 electrons becomes 2 I negatives. The potential of that reaction happening, as we saw, is a positive 0.536 volts. That means this other reaction, folks, must be an oxidation reaction, so we have to write it backwards. So we would end up with Fe becoming Fe2+ and 2 electrons. Now the potential of that happening is the opposite of the reduction potential, so that would be a positive 0.447 volts. Now when we add these reactions together, the 2 gained are canceled out by the 2 lost, so we end up with I2, let's see, plus Fe reacts to form Fe2+ and 2 I negative. Oh, I forgot the negative sign up there. And you can see that the charge on the reactant side is neutral, and the charge on the product side, when we have the 2 positives and the 2 negatives added together, is also neutral. We can add these voltages together to find the overall potential of that battery. And so we get a 3 here, carry the 1, that's an 8. And then this becomes 5. Okay, hopefully I did my math right. And we have a 0.983 volt battery. Okay, then we can determine the overall cell reaction and the standard cell potential, which you're going to see we've already done. And we're going to describe the cell using a cell notation or an abbreviated cell notation. So obviously, my overall cell reaction was just given here. That's I2 plus Fe becomes Fe2 plus and 2I negatives. My overall cell potential we just found right there was a positive 0.983 volts. Now my cell notation, we're going to start by drawing two lines that are parallel to each other, the written vertically. And then on the left side, I'm going to write an abbreviated form of my oxidation reaction. And in that process, Fe became Fe2+. And then on the other side of those parallel lines, I'm going to write an abbreviated form of my reduction reaction, and that's where I2 became 2I negatives. So this is called the abbreviated cell notation, and we'll master that shortly. Okay? All right, we'll see you kiddos soon. Bye-bye.